Hi, Chem 212 students, and welcome to our third and final lecture video for this week. It's all about cyclic alkanes. And so, as you may recall, carbon atoms in alkanes are sp3 hybridized, meaning, they're making 4 bonds and they have no lone pairs. And so they require 4 equivalent hybridized orbitals. So 1s and 3p orbitals are hybridized to produce 4 equivalent sp3 bonding orbitals according to valence bond theory. So when we have this arrangement, the arrangement is tetrahedral in bonding shape, and the bond angle is approximately 109.5. And so we can see here, for example, if we're just looking at methane, it is tetrahedral. This is tetrahedral right here, and every angle here is 109.5. Now, when a molecule ends up in a ring, when the carbons bond in a ring, well, that bond angle may not be 60 anymore. It may be forced into a different bonding angle. And so here, for example, if I wanted to make a cyclopropane with these, I could not use the standard bonds because I have to really bend them to get into a. So you can see this here. If I try to bond this one, if I try to bond this carbon to this one, you can really see the strain of trying to put this into this, because it doesn't want to be in that orientation. The natural orientation where the bonds are as far apart as they can be from each other is 109.5. Otherwise, the electrons are repelling each other when they get this close, and so you get what's known as ring strain when you try to when the carbon atoms are making bonds that restrict their bond angle to bond angles that are very different than 109.5. Now, if molecules were flat, what bond angles would you expect? Well, it would be 60 for cyclopropane, 90 for cyclobutane, 108 for cyclopentane, 120 for cyclohexane, and so forth. However, real molecules are not flat necessarily. They're in 3 dimensions, and so these are not the actual bond angles that are exhibited in these molecules. Except for cyclopropane, there's really no way for it to go out of a flat arrangement. So the cyclopropane is accurate, but the rest of these, they tend to pucker and make these kind of non-flat shapes. So here is what it looks like for cyclohexane. You get this non-flat type of shape to it. Okay. All right. So if we want to know the relative stabilities of molecules, well, we can do just what we've done before. We can talk about, well, how much energy is produced when these things are burned, when they're combusted. And now the number of carbons does matter, so it's not a direct comparison like we had for isomers where they had exactly the same number of carbon atoms. So what we do is we compare the amount of energy per carbon and 2 hydrogens that we've got. And so these are cyclic, so they all have 2 carbons per hydrogen. And because if you bond around in any cyclic arrangement, if you're bonding around in any cyclic arrangement, you're going to have the situation where there's just 2 hydrogens, or if it's only hydrogens and carbon, it'll be 2 hydrogens on every carbon. So we take this, the energy burnt by burning cyclopropane, and divide it by 3 to get the energy per number of CH2s. Okay, and you can see that energy of combustion is the highest for cyclopropane. It's less for cyclobutane, less for cyclopentane, less for cyclohexane, but then it rises again in cycloheptane. And this is indicating that cyclohexane has the lowest ring strain, and cyclopentane is very close. Then it starts getting larger. You can see that once it gets to cyclodecane, it drops again. There's a few drops here. And this is because in real life, these molecules can bend and move around, and for when they get large enough, they have a lot of ability to bend into a shape that allows for approximately 109.5 degree angles. You can see cyclodecane is actually more stable than cyclooctane. and cycloheptane. So why does it make the molecule less stable to have angles like this? Well, you can see it from that example that I was showing you. If you try, if it's bonded in that arrangement, there's a ring strain, and the ring wants to pop open like that. And so that's what makes the molecule less stable. If it has a angle greater than 109.5, what that means is it's kind of bending like this, but it wants to return to its 109.5 degree angle. And when I say wants to, the reason why is because of the repulsion between the electrons in the bonds. When you have a short angle, these bonds are getting too close to each other. They repel. When you have a wide bond angle, the bond angle between the hydrogens and the carbons gets smaller, and so they repel. So ring strain is due to the angle and also due to other factors. Cyclopropane. So cyclopropane is a flat triangle molecule. The angles are 60 degrees, which is much less than the favored 109.5. So these are, cyclopropane is quite reactive, quite unstable. And this is going to actually be taken advantage of sometimes in other reactions that we look at later. So not only is there a ring strain due to the angle, there's also a torsional strain in cyclopropane due to the many eclipsed hydrogen interactions. So these hydrogens here are all eclipsed, and so the result is that they have these eclipsing interactions as well, like the ones that we saw previously, and so this results in an overall very unstable arrangement. Cyclobutane is significantly more stable than cyclopropane. Why? Well, it's because it gets to adopt this non-planar puckered configuration, which expands this angle a little bit. We would expect this angle to be approximately 90 degrees if it were a flat square, right? It's a little smaller than that, but these other angles are bigger. So angle strain results from the bond angles of 88, which is not severe as 60 degrees. But this ring shape puckers to avoid the torsional strain of having hydrogens that are right next to one another and in an eclipsed formation here. Cyclopentane is very close to the stability of cyclohexane. Only 5 kilojoules per mole less, and it's because the angle strain is quite small. The angles are almost 109.5. There's a little bit of torsional strain. You can see it with these hydrogens. You can see these hydrogens here are kind of close to one another, but mainly they're staggered. So you can see there's a lot of staggering, like this hydrogen is staggered between these ones. There's a little torsional strain because of these hydrogens here. These are going to be what we call 1,3 diaxial interactions later. And so it makes this bent shape to avoid having more torsional strain over here on these sides. Finally, the most stable ring structure is the cyclohexane. So with cyclohexane, it adopts what's known as a boat conformation, and for this one, a chair conformation being the most stable conformation here. And for this one, I like to use mole view. So mole view to kind of visualize that. So mole view is a great tool for visualizing these structures. So I'm going to get rid of this. I'm going to put in a cyclohexane. I'm going to go 2D to 3D, and there you go. And so you can see this chair conformation, this being the most stable arrangement. And what you can see here is that when you look down each of these carbon atoms, notice how there's a staggered conformation. Here, if we look down here, staggered. Everything's staggered. The only steric strain that we have, or torsional strain, is that there's an eclipsing interaction that's farther away. and that's only happens on the so-called, what are going to be called the axial position. So you can also see there's two positions in this structure. There's the position where things are pointing straight up and down. These are referred to as the axial positions. And there's a position where they're kind of pointing outwards, out away from the ring. This is called the equatorial position. And so the goal of today, besides understanding these, is also to be able to draw these structures in such a way, this chair structure in particular, such that we can note where these 1,3 diaxial interactions occur. And so you can see this, it's not really a chair, it's kind of like a recliner chair, the chair configuration. And so, but that's what we've got here. And you can also, you know, if you've got your own models, like I did recommend to you guys that you probably want to get some models that you can hold like I have here. It really helps to kind of understand these positions a little more. And so I can build a 6-membered carbon ring, a cyclohexane, and there it is. So I've got one. And so the chair configuration, it looks kind of like this. And so you can see here that right now the purple atom here, it's in the equatorial position. It's kind of sticking outwards. But these chairs are they don't stay like this exactly. They can do what's known as a chair flip that we're going to talk about. And when they do, now this purple one is in the equatorial, or the axial position rather, pointing straight up and down, right? And so when this chair flip happens, we can have a flip from equatorial to axial position. And so this is, things like this is why these models are very useful when you're doing this. Another possible configuration is the boat. So the boat is where we have essentially like this. Both sides are sticking up like that, or sticking down. We got these two carbons here sticking up. So in the boat configuration, there's no angle strain. It's all 109.5, just like the chair configuration. However, there is more torsional strain because there's going to be more eclipsing interactions between the hydrogens. And so when we look at this boat configuration, we can see these right here are obviously eclipsing. So we've got eclipsing here as well. So 1, 2, and then 3, 4. These are going to be eclipsing, and so there's a torsional strain, and there's also a steric strain due to these flagpole or diaxial interactions as well. And so there's this conformation is a lot is less stable than the chair. So the boat is pretty stable because it has no angle strain, but it's not as good as the chair, which reduces the torsional strain significantly. As we saw from our Molview model, there's all offset staggered hydrogens instead of eclipsing hydrogens. So in terms of the relative energies of the conformations, what are they? So the chair is the lowest energy conformation. It has no torsional strain, no angle, no ring strain. It's very stable. If we go to a half chair, so if we have a chair here and we go to a half chair, which is where this is in the plane like that, that's a half chair. And assuming these are all hydrogens, so I'm not showing all the hydrogens, but there's a chair. That's 45 kilojoules per mole less stable than the chair conformation. Then we can have a kind of twisted boat, which is hard to show, but it's something like this, twisted boat. It's shown good by this drawing, which is 23 kilojoules per mole less stable than the chair. The boat is 30 kilojoules per mole less stable than the chair. The reason why the twisted boat is more stable than the boat is because by twisting it reduces some of the eclipsing hydrogen interactions. It alleviates some of this torsional strain. And then we go back to the half chair, then we're back to the chair. And this whole process of flipping here, see how the chair looks different? That is the chair flip that I was showing you. So here's the chair, and then we go to the half chair. Okay, it's partially flipped. Then we go to the boat. It's halfway flipped, and now we go to the completely flipped chair. And now the top one's on this side, bottom one's, and that's called a chair flip. So we're going to have to practice drawing these on paper, and the way that you draw them is you notice that these two opposite ends are parallel to each other. These two are parallel to each other, and these two are parallel to each other. So when you draw these, you're going to want to go like this, and notice they're slightly offset. So this point's a little bit higher than this one, like that. Okay, I like to draw that one first, and then this one second. So, and remember the last one is going to look the shortest. So these are parallel as well. We go like that, try to make them equal length. Then the last one is generally drawn as the shortest from the perspective here. Okay, and then when you draw this, you're going to have on either end, you're going to have a hydrogen that is axial, pointing up on the end one and down on the other end, on the downward. So on the downward siding point of the chair, there's a straight downward axial position, and there's a straight upward axial position. Then the way the axial positions work is they go up, down, up, down. So the second axial position is down here, the third is up, then this is down, then this one's up, and this one's down. And this is where we're going to see the so-called 1-3 diaxial interaction right here. 1-3, because if we call this number 1, it would be 2, 3. And if these get big, if these are big atoms or big groups, they're going to have an interaction. And so this would be the wrong way. Remember, the down side of the chair, it has the downward axial. And so these are all the axial positions. Okay, they go straight up and down. Now in terms of equatorial positions, oops, I drew it on the words there. Now in terms of the equatorial positions, so if we're looking at this structure, our axial positions are here, 1. So we go up and down, down on the downside, up on the upside, and then we go up, down, up, down, up, down, like that. And then for the axial positions, these black ones here are parallel to the sides. These ones on the end are parallel to these ones in the middle. And then these ones here on the connected to the right next to the ends, these are parallel to the small parts right here. And so all together with all the axial groups shown, we go up here, down here, and then it's up, down for all the axial groups. And then again, these axial groups here are parallel to this right here. These axial groups here are parallel to the sides. The ones in the middle are parallel to the sides. And these axial groups on the ends are parallel to this part of them. And that's the full structure, the way you can draw a cyclohexane on a piece of paper. Now, I'll show you this with the, I'll put a couple hydrogens in here to show you what this looks like on the ring, on a model here. So here are the end ones. These straight up, straight down like that. And then if we have, here's the equatorial one, and here's the axial. The axial one, see, the axial one would go straight down. Now, something I want you to notice is when you do a chair flip, the positions switch. So now, do a chair flip, up, down like that. Now, this one that was equatorial is now axial. And the two ones on the ends that were axial are now equatorial. The axial positions would be here now. Here. Here. So you can see how they switch places. So now these two are axial, and now when we do a chair flip, they move to the equatorial positions, and the other ones move to the axial positions. And you can see this one here. So look at this one here. Axial, right? Or equatorial rather. Then we do a chair flip, and when it's done, it's axial. And the 1,3 diaxial interactions are going to be for the two axials that are 1 carbon away, right here. If these are big, they're going to bump into each other and cause steric strain. So the vast majority of cyclohexane molecules will exist in a chair conformation because it's vastly more stable. I mean, look at this. It's even more of a big difference than the eclipsed hydrogen interactions. It's a huge difference relative to those. So whereas, you know, we had a 12 kilojoule per mole difference, that led to 99% more of the stable structure. With a 45 kilojoule per mole difference, it's going to be almost all of the cyclohexane at any given moment will be in the chair conformation. But they can flip. If they get warm, especially, they tend to flip. And so these axial and equatorial positions will flip, as I showed you on the model. When the chair flips, the axial position becomes the equatorial position. Flipping a chair is not like flipping a pancake. You're not just flipping it upside down. You saw the difference is that it goes through like this, right? It's just a turning of the bonds. It's essentially all the bonds are turning and rotating, and so it's not flipping it like that, right? And so when you can also view this through a Newman projection. So the Newman projection has 6 carbons. But when we're looking at a Newman projection like that, we're looking basically with these two being the front carbons, these, and then we have the back carbons are these ones here, and then we have these ones in the middle. So it's like actually like this. So front carbons, back carbons, middle carbon. Notice one is up, and according to that, the back one is up and the bottom one is down. But when you do a ring flip, so now what they're going to do is show you with the Newman projection, the ring flip. Now the front one is going to go up, and the back one's going to go down. So that's what's being shown in the chair flip there. And the axial and equatorial switch. Now this equatorial one, it moved down here, it's now axial, and this hydrogen moved over here, it's equatorial. But as it says here, chair flipping is a lot easier to see with a handheld model. So you may want to get some of these if it helps. Now, when they were all hydrogens, both versions of the chair were equally stable. However, what if we replace one of the hydrogens now with a methyl group? And so this methyl group is much bigger, it's going to be much bigger than any of the hydrogens. And so there's going to be some steric strain that arises. There's going to be some steric strain that arises because if we're filling in other hydrogens here, especially these ones, these axial ones right here, which I'm about to put in, so notice that when this methyl is axial in this model, this hydrogen can get very, very close to these other hydrogens. It's extremely close. And these are 1 carbon away. They're all axial. And so this is going to be what's referred to as a 1,3 diaxial interaction. And there's going to be steric strain due to this. When it comes to the relative stability, this is unstable due to the 1,3 diaxial interactions. Notice what happens if it chair flips, though. Now the methyl group is equatorial. It's sticking way out here. It's not having the same type of interactions with other things. There are hydrogens here that I didn't put, but this is way out here. It's not interacting as much. So the equatorial methyl is much more stable than the axial methyl because it doesn't have those 1,3 diaxial interactions. So it causes a torsional strain, or it doesn't. Rather, it doesn't cause an angular or torsional strain. It causes a steric strain. So the steric strain is due to the crowding of the atoms. And so when the methyl is on the axial position, it's crowding with the other atoms, the other hydrogen atoms. Here's the real model. Here's the flat paper model. And so this is referred to as 1,3 diaxial strain. And that strain doesn't exist when the methyl group is equatorial, only when it's axial. So the 1,3 diaxial interactions are equivalent to a gauche interaction in terms of energy. And so remember that was 3.8 kilojoules per mole of energy cost. And so you can see this this situation here. Essentially, this methyl group is gauche to this CH3 group. And so we have this steric strain. It's steric strain because they're occupying close positions. They're crowded, the atoms. But the equatorial position is equivalent to anti. So anti meaning, see this carbon CH3, or this carbon here, is opposite position of the CH3 once the ring flip has happened. However, here it's 60 degrees with the gauche interaction. So other large groups, not just methyl, but other large groups will cause steric crowding in the axial position. And here are their relative energy costs. You don't have to memorize this, okay? These numbers will be provided for you if you need them. I will provide all these energy numbers. I just simply expect you to be able to use them. Memorizing them isn't really that important to me. And here's the ratio. So when you have an energy difference of 4.2 kilojoules, you get this ratio of structures 83% more stable with the equatorial position, or OH here, 17% in the axial position. And as it gets larger, the ratio gets greater. So now when you have multiple substituents, though, you may have to add up one more thing is, notice the CH3 is actually gauche twice. And so this 7.6 is 2 times 3.8 kilojoules. 2 gauche interactions at once when there's an axial methyl. Now when you got multiple substituents, you can either use wedges and dashes to show their axial and equatorial positions, or their relative positions up and down. But if you do this flat structure, it doesn't show the axial and equatorial positions. But notice that if one is up and the neighboring one is down, remember the axial positions go up, down, up, down. So if we have the chlorine here at the up position, if methyl is a dash here, that means it's at the down position. And so it's also axial. The up position is axial here, the down position is axial here, the up position is axial here, and so forth. And if we do a ring flip, both of these axial positions become equatorial. But still, the chlorine is on the top side of the ring, indicated by the wedge here. And the methyl is on the bottom side of the ring, indicated by the dash here. An up substituent can be axial or equatorial, depends on how the ring is flipped, right? But relative to one another, the chlorine and the methyl will have the same axial or equatorial position because of the way they're arranged. One is up and one is down. Okay, so let's look at these chair conformations. So now the ethyl is the up position, the methyl is the down position. So let's say we draw a chair and we put the ethyl up. Okay, in terms of axial positions, so these are the axial positions. I'm just going to draw all the axial positions in red. Up, down, up, down, up, down. These are all the axial positions. Okay, notice that ethyl, and I'll draw the equatorial positions too. Let's draw them. Okay, equatorial. This one is parallel with this right here. Okay. And then this one right here is parallel as well with these. Okay. And then this one here is parallel. They're basically parallel with the things that are space away. So this will be parallel right here, and this would be parallel to this one right here. And this is going to take some practice, guys, right? And then we got this is the equatorial position here, and this is the equatorial position here. This is the axial one. So because the methyl is in the down position, it must be equatorial if the ethyl is axial here. So because axial goes up, down, up. So the axial position is up here, but the methyl position is down, so it must be on the equatorial. Now if you do a ring flip, methyl's still down. However, so that's this carbon here. However, it's axial now. And ethyl is still up. I mean, the hydrogen is right here. This is the hydrogen here. And this one is the hydrogen here. So the hydrogen is in the down position here, the ethyl is in the up, but the ethyl is equatorial. The hydrogen here is in the up position, the methyl is in the down position, but now it's axial due to the chair flip. Let's do a similar analysis for the following molecule. Again, I encourage you to pause the video and give this a shot for yourself. Don't give up this chance to try it out, and then I'll show you the answer. So pause. Okay, I'm going to show you the answer now. All right, so we're going to first start by drawing a chair conformation. Whoops. We're going to draw a chair conformation. So we draw the two parallel ones right here. Then we draw two longish parallel ones right here. And then these ones are the shortest ones right there. Okay. And I'm gonna give the ethyl the axial position here. Okay, up. So remember, axial is up, down, up. But the chlorine's in the down position. So it's going to be let's see. Oh, I thought I had blue there. Down, up, down. That's where the chlorine is. Okay. And we can do a chair flip. So if we do a chair flip now, this will be up like that. Okay. We'll go like this. And then that. Okay. And now the chlorine will be let's see, this, so this is the atom, and that's now up, so the chlorine is right here. So now the axial positions will be up, down. So the chlorine here is now in the axial position. Okay, up, down, down. And the equatorial positions, now the ethyl is over here, it's in the equatorial position. Notice that it's still up. It's on the top of the ring. The hydrogen is down at the bottom. However, it's in the equatorial position now, and chlorine is in the axial. Now, because rings have a side, a top and a bottom, there's also such a thing for, there's also stereoisomerism, in particular, Cis-Trans Isomerism. So, cis is meaning the same side cis. So if both methyls on a ring here are both groups, whatever they are, on the same side, we say cis. So it's not enough here to say 1,2-dimethyl cyclohexane. We have to say cis because that's indicating the methyls are on the same side, both on the top. As opposed to trans 1,2-dimethyl cyclohexane. Here, one methyl is up and one methyl is down. So these are not constitutional isomers because the atoms are not bonded in a different way. The first carbon is bonded to a methyl. The second carbon's also bonded to a methyl. They're just in different positions. This kind of isomerism is called stereoisomerism. Stereoisomers. These means isomers that have the same bonding arrangement, but their atoms are positioned differently in 3D space. Okay, and that's what's going on here. These atoms, these methyls are positioned. They're not bonded to different other carbons. They're just positioned in a different way in 3-dimensional. Finally, there are polycyclic systems. So there are molecules that have multiple rings in them. And so we've seen a couple of examples of this when we named. I only have you name very simple bicyclic systems like this, but we took a look at those. Bicyclic arrangements are common in biomolecules. Camphor and campine, for example, are fragrant natural products. You can get them from evergreens. They come from, you can smell them, pine trees and stuff. There's also multiple cyclohexanes that can bond all together and make very large structures. So diamond is like that. Diamond is just a bunch of carbons tetrahedrally bonded to all other carbons. And they make these arrangements that ultimately lead to rings of 6. Another molecule here with a common name called decalin has 2 cyclohexanes stuck together, basically. These are important molecules as well. You get lots of multi-ring type of molecules in biology. For example, steroids. Steroids are generally formed from a cyclohexane that is attached to another cyclohexane. I hope I'm remembering this exactly right. Let me just look it up. For some reason, I'm doubting myself here. But if we look at cholesterol, for example, here's cholesterol. So yeah, and so you've got a cyclohexane ring here, another one maybe has a double bond or something, another one, and then a 5-membered carbon ring. So these polycyclic systems are very common in oh, they're right here. I had it. So the steroid hormones are right here. Here's testosterone, estradiol. So the steroid hormones have a very predictable polycyclic arrangement. And so that's going to be it for alkanes. I hope these lectures were useful for you, and please let me know if you have any questions.